Hello, everyone. This is Mark Drugenti with Burt Process Equipment. I'm the Director of Design Engineering. I want to welcome everyone today for joining us on this webinar. Today we're going to be discussing both ChemPlus, chemical injection-based systems, as well as PolymerPlus polymer injection systems. And just a couple of announcements as we get started. We do have a questions box that you should all have access to for chat. Feel free to type any questions in as we go along. We'll try to answer some questions during the broadcast, and whatever we don't get to, we will certainly discuss at the end of the broadcast. If we run out of time, then we will answer any questions via email after the presentation. There will be a brief follow-up to come out after the webinar, which we're asking for your guys' feedback, what your guys' thoughts are, and also what you'd like to see from the future educational series. So without ado, let's kind of get into this. So we're going to kind of talk about this presentation really in two different sections, because while chemical feed and polymer activation and feed are related and they're used in a lot of very similar applications, they are slightly different as far as systems are concerned. So we're going to kind of focus sort of in the first part of the presentation on polymer, on the PolymerPlus, polymer activation and injection systems. And then we're going to focus in the second half of the presentation more on chemical feed and chemical injection systems. So talking about polymer systems in general, what a polymer system does is it takes a polymer, and a polymer are essentially long chain molecules, and polymers come in a lot of different forms, but what we're really talking about today is polymers that are essentially used to colloidal or basically as magnets attract and suspend particulates, thereby forming a larger solid. This is a very common thing that comes up in different forms of wastewater treatment, metals precipitation, and other types of applications where you just simply have a particulate that you're trying to remove, which is simply just too small for conventional treatment. So you add these polymers in, and as a result of that, you can then add this larger suspension, which ultimately kind of looks like this kind of like cloudy substance, essentially, where you have additional mass, which allows you to have filtration. The thing with polymers is polymers, because of this, because of their interaction with water, as well as colloidal matter, need to be kept in a form that allows them to not interact before their actual use. As such, they are typically immersed in some form of an oil. So they need to be stripped of that, and they also need to be activated or elongated. Polymers, you kind of think about like a long strand of spaghetti. So when you have have your colander, they're full of spaghetti, you have all these things kind of wound together. What you want to do is activate them so they open up, and then that allows them to basically act to their full potential and bind to the actual constituents that you're trying to target within your system. But because of that, they're also fairly fragile. So polymers, you can kind of see here on the screen, going from left to right. If you have insufficient mixing, if you try to actually pull your spaghetti strands apart and you don't do it enough, they really don't open up sufficiently to allow for proper use in your water system. As such, you have to do a lot of overdosing of your polymer to achieve the desired performance. If you overactivate them or you put too much energy in, they're very fragile and they'll basically break apart. And then at that point, you still end up with the same result, which is overdosing and wasting a lot of chemical. What you really want to achieve is a balance where you get that sufficient amount of energy to strip that oil off and then fully activate them so they end up with nice kind of long strands when they're injected into your system or into your waste stream to allow for that proper activation and targeting of the suspended solids. So the process of activation of an emulsion polymer involves stripping the oil off the polymer molecule and exposing the polymer to water. So really in most systems, what you're really doing is you have the polymer, which is going to be done in some fairly low concentrations ultimately. You generally don't use a lot of polymer, and anybody who's ever used polymer in the field, or even if you're in a swimming pool and you put polymer in, Overdosing polymer is very bad because then what happens is you end up with this very cloudy, basically base water where you just have polymer essentially floating in there. So what you're doing is you are diluting it into a water stream, and then that water stream is then stripped of the oil. You strip it of the oil, you introduce it into that water stream, and then you activate it. That's kind of the process by which polymer systems work. So really you have a chemical injection into then a dilution-based stream, which allows you to then inject it into for actual usage. So at the moment the polymer is exposed to water, sufficient energy has to be added to quickly disperse the molecules and strip the oil off. If that does not occur, like we saw in the previous slide, or too much activation occurs, then you end up with a problem with the polymers either under or overactivated or exposed in those cases. That's what a polymer activation dilution injection system looks like. And what you basically have here is this is your polymer pump, where you're basically injecting in your polymer, whether it's a metering style pump, a progressive stavity style pump, or a peristaltic style pump. And this is where your water feed comes in here. Now, whether that water feed is sufficient, you have enough pressure, you can definitely add a booster pump onto that to basically increase the pressure coming in. That is basically injected and diluted, and then it comes up here, which is actually where your polymer activation chamber is. And there are a couple different ways to do that. In Burt process equipment, we utilize what's referred to as a motorless activation. In a sense, what's happening here is as the polymer and the water are combining, you're basically putting them through a very fine opening that basically causes them to accelerate to a very rapid velocity of about 40 feet per second. Almost kind of like a spray nozzle setup, but a little bit different, basically like a venturi at that point, that generates a fair amount of turbulence to allow for sufficient activation of your polymer. So this is really what's going on here. You can see it on the screen, what's going on in that activation chamber. As you get sufficient pressure, you push open the opening here, you get that basically hydraulic spin, increase the velocity and the turbulence, and you end up with a well-activated polymer in that case. And there is a little bit of changes. There's obviously the amount of polymer you're using also depends on the type of polymer that you want to use in a lot of situations, and the flow rates. There's other kind of variables that go in there, but mechanically speaking, this is how a polymer activation system operates. So motorless activation, you're trying to achieve a very, very fast velocity for both your polymer and your chemistry, but because there's actually no moving parts in there, you don't have an agitation device or a mixer or an impeller, you're not going to get that kind of polymer shredding that you oftentimes do see in a polymer-based system. Obviously, you want to achieve an ultra-high energy and expose the energy only once. Once you essentially activate the polymer, you then don't want to be putting more pressure. You then don't want to necessarily be pumping it again or putting in additional energy. Now you risk overexposing and essentially breaking down your polymer even further. Before we move on to the next section, we're going to have a quick poll here. If anybody would like to participate in that, and we'll give you guys about a minute or so to answer that. Okay, so the poll question was, what is the advantage of proper polymer activation? The choice A, does not require overdosing, B, broken polymer chains, C, polymer gelling, or D, achieves the most active sites. Obviously, the advantage of proper polymer activation is that it achieves the most active sites. Overdosing of the polymer is obviously what you want to try to avoid. Broken polymer chains are less efficient, and polymer gelling is just really another term for when the polymer is not fully activated. It's still kind of like stuck together to itself in that case. So obviously, really what you're trying to achieve here in the polymer activation step is to achieve the most active sites or the most high energy version of the polymer that you can. However, in some cases, and I know there is some variance across the industry when it comes to this. Some people do like to have both a non-mechanical as well as a mechanical, or have a dual activation to a polymer to a polymer system. So in that case, beyond just a hydrodynamic activation, which we just talked about, in some cases people also use a hydromechanical or motor-operated system in tangent. And this really depends on the type of polymer that you're working with. And polymer selection is kind of its own, essentially, area where you have to kind of look at, because really what it comes down to is anionic, cationic, neutral. It depends on what kind of species, the water chemistries that are involved in the system. And that's kind of a whole different area that would really be kind of a separate presentation. So we're not going to really focus on that too much here. But definitely, to know that there is sometimes polymers or different chemistries that will actually require, some people just prefer to have that dual stage activation in that case. And the most common one is going to be some kind of a high speed impeller at that point. So you come out of your hydrodynamic activation at 40 feet per second, go through that impeller-based second activation step, and you really, at that point, you've put a considerable amount of energy into your system to allow for full polymer activation in that case. So I talked about this a little bit earlier, what really goes into the full polymer-based system. And the polymer-based system, again, is a form of chemical feed. And this is really an example of a liquid polymer system. We'll talk a little bit about solid polymer systems and kind of the pros and cons between those here in a moment. But the features that are involved, you're going to have a liquid polymer operate based on, you can basically bring in any type of water source, whether it's potable or filtered water. You're going to have a flow switch or some kind of enunciation that you do have sufficient flow, and in many cases sufficient pressure from your water source. And booster pumps are sometimes common with these to allow for that sufficient pressure of water for your polymer to be injected into. You're going to have your activation chamber, and these have a lot of different options. And generally speaking, polymer flow rates, they range from very low, fractional gallons per day, and going up to 500 to 600 gallons per day. That's a lot of polymer. Obviously, that's a very big system. Polymer is used in a lot less volume than many other chemicals, which are commonly associated with chemical feed. And the most common types of pumps utilized are going to be solenoid diaphragm, such as the one shown here on the slide. Peristaltic, or in many cases progressive cavity pumps, are also very good because they allow for good movement and fairly high flow of the polymer. Talking about this from a P&ID standpoint here. This is where your water comes in and goes through your strainer and solenoid valve. You have your low water switch, your metering pump injection coming up here. You're monitoring your flow, so it matches what you have from your metering pump, and then you go through your activation. This is where you have your hydrodynamic system, and then this is just a site class where you go out for your active discharge. Progressive cavity pump design is very similar in this case, obviously used for higher flow. This is your solenoid water feed, and then you have your progressive cavity style pump here, which leads to, again, a very similar results. Again, progressive cavity tends to be utilized on systems that have a higher flow requirements than something like a metering pump application in those cases. There are a lot of different options that can be implemented into these systems. And this is very true of a lot of different types of chemical feed systems. You can have you can have polymer switch monitoring and flow rates. Sometimes these have to be installed in explosion-proof environments. This is very common in the oil and gas industry, or if you have particularly high amounts of methane present in the area where you'll be using this. You can have aging and blending chambers. Some people like to have that where after you've activated the polymer, you put it into a tank at that point and then allow it to basically sit for some predetermined amount of time. This is what's referred to as aging in that case. And Some polymers respond better to aging than others. Some people say it's unnecessary. There is more equipment obviously involved. So you have to kind of weigh the pros and cons between having an aging system or not at the end of the system. Obviously, higher flow rates, pressure, increased city water pressure pumps, and then very often these are utilized in municipal applications. So they can be tied into SCADA-based systems, or they can be PLC operated themselves. Just one quick example here that you can see. This is a dual setup polymer feed system. This system has secondary containment with a flow of 15 gallons per hour for clarifier application of a 0.25% polymer injection system. This is utilized here at a wastewater treatment plant located not far from our corporate headquarters here in Hamden, Connecticut. And one of their primary concerns, obviously, was redundancy in these types of systems. Obviously, if you're dealing in a wastewater industry that's going to be running 24/7, having that level of redundancy built into your system can be very important as well. And we're going to see that a lot more, obviously, when we start talking about the chemical feed systems here in a couple of minutes. Thus far, we've really focused on liquid feed systems, but dry polymer is also used, and some people do have a preference for it. Dry polymer operates a little bit differently in that you're not trying to necessarily activate it in quite the same way or strip off the oil, but now you're basically going through like a dilution-based system, which then obviously goes into either a tank or some kind of a blending and aging chamber prior to use. There are kind of pros and cons to both of these. Obviously, liquid polymer, there is a shelf life associated with it. So you do have chemical drums that you need to maintain. Talking about solids, you can hold a lot more solid polymer for a lot longer, but you do have to be concerned about humidity impacting that. If you do have a high humidity environment, solid polymer can begin to interact with itself before you even get a chance to utilize it within your actual system. So one of the most common methods of injecting the polymer is what's referred to as basically a high-speed inductor. So you have this water stream coming through. You have a dry polymer base now, which is being injected into your system at a very high velocity. And this basically allows the polymer to basically be dissolved very rapidly without the need for clumping or then sticking into the actual venturi where it's actually put into the actual water. And this is fed either by like an auger-based system, where you're basically going to have like a hopper that you're going to be basically pulling out of these types of things through an auger base, and then it's fed directly into that high-speed eductor. Or is more of a disc-based system where you're basically using like a vacuum, and essentially you're pulling the dry polymer out of there. Again, you still have a hopper-based system, but you have basically the polymer is fed and then ultimately drawn through into a vacuum eductor, which then goes into that high-speed venturi at that point to allow for activation and then use. Just a couple of quick examples here of how these are operated. You can see here on the left, you have a dry polymer feeder where you have more of like a disc-based design where you're drawing off into your eductor. This is again your city water feed. Dry polymers almost always have an aging-based tank, and then you basically have another tank which then you have to then pump the polymer in for actual use. This one here, this is an auger-based design, again, very similar in this case, but in this case, you're doing a mixing, aging, and all pumping basically as like one section at that point. So that's really kind of, the two different looks at how polymer systems tend to be tied together, liquid versus solid. Liquid, obviously, you have the activation step that's involved, and then in the dilution with solids, obviously, you have a bit more equipment based, but there are pros to utilizing it that way. But then you'll be drawing into more of a vacuum-based design. And again, regardless of them, the basic polymer selection chemistry is very important, specifically targeting what you're trying to do as far as actually colloidal collectment or particulate targeting within your system. And achieving the optimal polymer activation and aging is really what defines that when it comes to polymer-based injection systems. Switching gears now, and we kind of move into sort of the second part of the presentation, we're going to talk a little bit about chemical feed systems. So, in the realm of chemical injection systems, polymer feed is probably about 5% of the entire chemical injection, really repertoire that people are basically used to. In a lot of ways, broad-based chemical feed is the other 95%. So, what is chemical feed? Chemical feed runs a very, very broad category where you have some form of a pumping technology as part of a modular system, which is used to inject into a variety of applications. And what you're injecting, whether it be acids, bases, fluoride injection, disinfections, like hypochlorite or PAA, it really does run the gambit, and it runs the gambit across a number of different industries. And ChemFeed systems are really looked at kind of in sort of two related but also unique ways. The first is selecting the proper pumping technology that's going to be utilized in the system. And here, just in the opening slide, we have a couple of different chemical metering pump examples, but also the apparatuses that go along with that. As you can see, in the same image, you have calibration, pressure gauges, back pressure, pressure relief valves, pulsation dampeners, containments, safety of enclosures, and those really marrying those two concepts together is really what drives into making a fully functional chemical feed system. In here you can see a couple of different examples. Kind of regardless of the specific style of chemical feed system utilized, chemical feed systems have a lot of very similar components, which I just kind of went through here. You have here, you can see on the left, you have a chemical metering pump, whether that's just a chemical metering pump or different pumping technology. You're drawing your chemical. You have a strainer, isolation. You have your calibration columns here, pressure relief, back pressure valve to put pressure back on the pump, pulsation dampener, and then your injection valve. At its heart, 90% of chemical feed systems incorporate almost all, if not all, of these basic components into them. And where really the engineering comes into is how to build these to basically handle the chemicals that are involved. Some chemical injection works on very benign chemicals, and sometimes they work on very strong chemicals. And the right pumping technology and the right system for that, when the materials involved in that, how they're connected, gasket materials, that's really where a lot of the engineering comes into how to actually build a chemical feed system from the ground up. So I mentioned earlier, where's ChemFeed used? Disinfection, pH, fluoride, whether you're talking about all kinds of different areas. Wastewater, food and beverage is a big one, clean in place. This is true of a lot, very large scale industrial, even from not just food and bev, but if you have other kinds of general industry which is involved, or pharmaceutical wastewater treatment, there is a lot of different places where you can utilize different chemical feed equipment. As well as institutions, cooling towers, boiler treatment, closed loop, PCW systems. There really is a lot of different variation when it comes to chemical feed systems and their use. And that really what that use is, the chemical, that's really what helps dictate the pump selection and then ultimately the system selection, which is involved with these. As you kind of notice as we go through, we've seen a peristaltic pump, we see motor-driven metering pumps, air-operated diaphragm pumps, gear pumps, progressive cavity pumps, rotary low pumps. There's all kinds of different pumping technologies that can be utilized based on flow rates, the pressures, whether there's degassing requirements involved, the chemical compatibility that also plays into things like this. For example, here on the screen you can see you have all that white piping. That's all welded PVDF piping in that case. Obviously what the nature of your chemical is determines whether you want to use a PVC, CPVC, polypropylene, PVDF, polyvinyl difluoride, stainless steel, Hastelloy, welded connections versus threaded connections. A lot of that's basically driven by what the nature of your chemicals is in your system. So this is what a standard chemical feed system looks like. And you can see here on the right, you have, some kind of a thermoplastic, in this case, polyethylene deck. You have your isolation valves, the calibration columns, your pressure relief devices, pulsation dampeners, the back pressure valves off the pumps. Um, Again, a number of different pumping options we're going to talk about here in a couple of minutes. Piping, which I just kind of went through, varies based on the materials involved. Pressure gauges, and this is a standard kind of duplex configuration. They can also be modified. This is more of a triplex. Obviously, the pumps are missing from this example here, but it's fairly common to see either simplex, duplex, triplex, or more when it comes to chemical feed systems, because very often you really do need that redundancy. What you're actually utilizing, say it's a drinking water-based system, you need to make sure that you always have that you're always injecting chemical. These systems can tend to run very frequently, 24/7. So, Burt process, we have a standard-based system here. You can see a kind of 3D model here. This is kind of what we offer, which is a half-inch thick, polyethylene base, floor, wall, schedule, different piping selections, visual flow, containment. And one of the questions that comes up a lot is why would you look at a chemical feed package over, say, just a chemical feed pump, and then you can install it in the field? And really, the big answer to that question kind of lies in the idea of sole responsibility. So, as I mentioned before, really the heart of a chemical feed system is how do you, really how do you as an engineer, the end user, you have a chemical you need to inject, and what can happen is you can just select the pump and then kind of field build it yourself, or someone can sit there and do the pump selection for you based on what your flow parameters are. Look at that material compatibility that's involved in it, select the right piping material, go through the engineering and design, 3D drawings, do a full functional test of the system, hydro test it, implement different features we're going to talk about later, depending on how you're going to install it, whether it's inside or outside. And now you basically have someone who has sole responsibility in that case. So that's really the benefit of looking at a complete chem feed system over just a pump that then gets kind of installed in the field, is somebody has sole responsibility and solely has actually engineered and tested this system that they can use it in that case, that they can be implemented safely and effectively in that case. So in addition to that, there are a number of different options. As I mentioned, you have different pumping technologies, diaphragm, gear, peristaltic. Skid material can vary. Safety is also a big concern with a lot of these systems. Obviously, you are handling, in some cases, some very strong chemicals which are involved. And you can see here kind of in the video, there are ways to build different shields over these chemicals. Whether they're open door or more of just a clear PVC or Lexan, spill containment. And this is what you tend to see more when you're looking at more of an engineered based system. And all systems are fully factory hydro tested and designed. In addition, you can also move chemical feed into much more of a customized realm. And what I mean by customization is, beyond just what you would typically see as far as chemical injection, on a small base. These can be built into, as an engineered system, into much larger, for example, like containerized base design, integral safety showers, full PLC base, kind of full PLC base systems. Can also be implemented. Explosion-proof designs are also involved. For example, very commonly in the oil and gas industry, they do chemical with fertilizer. A lot of stuff is done more in terms of explosion-proof configurations or design. So there's a lot of ways to also implement that when looking at some different custom systems. And again, you can even integrate tanks into these systems. You have your full metering pump designs down here, and then you have your tanks, which you're basically drawing out, and then utilize within your actual system in this case. At this point here, we're going to do another poll question for those who are interested in it. Give you guys here about a minute or so. All right. So the poll question was, what kind of pumps can be used for chemical feed systems? Obviously, answer number one, metering pumps. Number two, air-operated diaphragm pumps. Number three, peristaltic. Number four, all of the above. Obviously, all of the above can be utilized in a chemical feed system. And again, it really does depend on the type of technology you're looking at, and type of pumps you want to utilize, the flow rates that are involved, and as well as the chemistries that are involved as well in your system. So we're going to talk about here, and we just have a little bit of a short video. This is one example of a system, but I really kind of want to walk you guys through, a full chemical feed system at this point, and then a little bit of the integration that was kind of put into it here. This one was utilized at a fertilizer plant in the Midwest, and you can see there the actual pumps there in operation. And this was built in a couple of different styles between PVDF, which is shown there in the system. There was a duplex as well as a triplex. And you have, again, the full polyethylene spill containment pan. You have the Y strainers, which you can see here in the video, which again, this is all PVDF piping in this space. You have the check valves for backflow prevention. Pulsation dampeners were located up here for this unit. And then you have your pressure gauges also as well. And then you had your back pressure valves also visible here in the system. And this is how the whole system was basically set up. They had very high pressure PVDF and stainless. And these had their own basically junction box designs. Controls can vary quite a bit with these different types of systems, whether it's going to be a full PLC control or more of a junction box design. And these systems were also installed outside. And they were, because of this, they had to be put into more of like an environmental based enclosure at that point. And to protect, obviously, thermoplastics, the equipment utilized very much in chemical feed systems, it's chemically resistant, it is not necessarily environmentally resistant. So while heat tracing is an option in some cases, based on the nature of the chemicals involved, as well as the material selections needed because of that, it was very critical to put these in more of an environmental enclosure like you've seen here, and obviously like we've seen through some of our other examples, looking through some of the customized base systems that that are utilized in the system. Majority of chemical feed systems are built in either a simplex design, a duplex design with S duplex lead lag or duplex redundancy, or as part of a triplex arrangement. And obviously, we've gone through many before, a lot of the different system options. From a P&ID perspective, you have the metering pump here. This is obviously for a simplex design. You have this is what I said about the check valve, the Y strainer. comes up into the pump. You have your calibration column, pulsation dampener, pressure relief, and then back pressure valves. Back pressure valves are somewhat common on a lot of especially on metering pump applications, because you want to get more of that consistency in the pump. So you want to put some artificial back pressure in there as well. Depending on the flow that's involved in the system, you can also see things like flow meters in the system. That's very true when we have very high flow applications going on as well. Duplex, obviously a lot of ChemFeed equipment is duplex for that level of redundancy which is involved in the system. Then you basically have this, you only have one calibration column, but you basically have everything else is basically duplex, so that if one train is essentially shut down, the other train takes over completely. It allows for complete chemical, allows for continuation of the injection, or the chemical basically being pumped into your system. Duplex lead lag is not as common. In this case, you basically just have two redundant pumps, but you have one shared discharge or one shared suction. This rarely comes up. This is really if you just want to have full redundancy as far as your pump selection is concerned. But it, again, is very similar to a duplex design, but you have you basically have redundancy in the pumps in that cases. And then obviously a triplex. You don't see much beyond a triplex. I think I've seen 6 pumps consecutive in a row once, but that's a very special application. Triplex tends to be the most common for if you want full redundancy in the system, where you essentially have 3, full trains that all share basically one common suction at that point. And it's not uncommon in a lot of applications to also see more than one chemical. If they're compatible, more than one chemical can be utilized in a system to allow it to operate. Basically from like one base. So you may sometimes see not chemicals obviously react, but you can see 3 pumps where 2 are a critical chemical, and then 1 pump on the triplex, which would then have a separate feed and calibration column in that case, could be utilized for another chemical at that point. So that is common, and that does come up from time to time as part of these systems. But in generally speaking, it is 1 chemical per base, but sometimes they do build longer ones that are designed to operate like that. As I mentioned, one of the primary benefits of really getting involved in looking at a chemical feed system as opposed to just looking at a pump is the system itself is fully tested and engineered, as a unit. And what that really means is, in that case, you have hydrostatically tested, pumps have all been checked out, everything's basically been tested, and you have an actual inspection report. This comes up a lot in municipal applications where people will try to just buy a pump and then essentially try to stick build around it in that case, and now you have multiple trades which are involved with that, and that can lead to a lot of issues when it comes to systems. So having one, completely built out, engineered and tested system allows for basically single source engineering and single source responsibility, when it comes to the application. And a lot of people do build chemical feed systems, and hopefully today we've kind of gone through a lot of sort of the pros and cons and different options. Obviously, this is a very broad topic, and specific chemical applications or specific chemical injections, PAA versus hypochlorite versus different chemicals. They kind of bring in their own challenges into this and different conversations as far as the pumps that can be utilized or the materials that can be utilized in that application. It is worth noting that these systems, they can be customized. They're not just a rigid design where you have a pump and a back pressure and a pressure relief valve. They can be built based on what goes on in them. They can be built based on the application, the environment, whether inside or outside. There's a lot that can be put into these to make them really suit a client's needs. So again, it's kind of mirroring the idea of the pump technology, which is utilized in the system, and then also the system design itself to build a complete chemical feed-based system. Just a few announcements here before we get to some of the questions. We do have a couple of additional webinars coming up at the second part of this year. We usually take the summer off, but we do have high purity water systems, which will be done on October 6th. And then we have custom engineered systems on November 10th. If anybody's any interest, you can certainly feel free to sign up for those as well. The registration is open at this time. And with that, we do have a few minutes here for questions. So we do have a few questions in the box, so I'll get started with those. If anybody has any additional questions, feel free to write them into the chat window, or you can certainly email us after the broadcast, and we'll get back to you. Again, there will be a brief survey sent out. So if you please complete that and send it back, that'd be greatly appreciated. The first question we have is, how is degassing or chemicals that require degassing impact chemical feed design? So for those of you who are aware, or those who are not aware, there are different chemicals that do off-gas quite frequently, the big one obviously being hypochlorites. And what happens is, especially when you have like a metering style or basically like a solenoid-driven metering pump, you can essentially get a gas bubble build up within the actual pump, which then chokes down or basically can stop the flow going through the actual system. And in a lot of cases, what people used to do was they used to have, and a lot of people still utilize this, but there's also been a lot more advances in the features, which are involved with these. They would have an off-gassing port coming off of the valve, which could then be used to bleed that gas. And all of the ball valves and equipment in the system would also be degassing valves in those cases. But as more and more smart metering pumps have kind of been designed, they basically implement different degassing features in them. And really, what those are is on basically a controlled basis, they'll basically pulsate the diaphragm at a very, very rapid pace, you're not actually pumping to basically drive the gas out of the system. So that's one of the things I'd recommend. It's kind of looking at more of a smart metering pump. There's been a lot of case studies done, and we've also used them to great success, where you do have a lot of that integral design. That you can actually just basically remove the gas. Otherwise, this has been obviously an ongoing problem for years because hypo was very commonly utilized. It still is, although there is now more competition to hypochlorite out there, things like peracetic acid, or even like chlorine dioxide, for example, are also gaining some steam in different applications. But by and large, hypochlorite is still one of the most common chemicals utilized, in chemical feed as well. How do you determine the piping materials to be utilized depending on the chemicals? So one thing to bear in mind, when talking about any kind of a chemical feed system, this really applies to more ChemFeed over, say, polymer feed in those cases. You can be handling some very strong chemicals. By and large, it depends on your application, depends on whether you're in more of a municipal application or industrial application. But you could be dealing with, hydrochloric acid at 37%. You could be dealing with different other chemicals that are very strong in those cases. Everything in your system, from the metering pump to the pump head, the valving, the gasketing, all of that, pressure gauges, any kind of meters, everything in that is going to be exposed to a very strong chemical, and a chemical is going to be primed in the line. It's going to be constantly exposed to it. So that's one of the big things to look at, and it's something that we take, something that we do a lot of review on is what can actually be utilized with basically a standing chemical, in the line for that amount of time. So there's been, a lot of things get looked at between either, EPDM, Viton, or even Teflon encapsulated, EPDM and Viton seals. The seals tend to be, looking more at piping tends to be a little bit simpler. You can look at it and say, okay, PVC versus CPVC versus PVDF, stainless, or even Hastelloy in some cases. But a lot of the issues to really review more in depth are going to be like the pump heads, the gaskets, and then why you want to be threaded or welded connections in a lot of those cases. That's the big thing from looking at what chemicals are involved. Again, the stronger the chemicals, and again, there can be a lot of diversity in chemicals. That's one of the bigger things that comes up very often in these systems. What is my preference between dry polymer and liquid polymer systems? Personally, I prefer liquid polymer systems over dry polymer. I've seen dry polymer have a lot of issues if it's not properly handled or stored. And I actually was a polymer chemist back long before I was the director of design engineering. And polymer does have the issue when it does be exposed to humidity of beginning to clump up itself, and that can impact its ability to be drawn as a solid. So if you do not have that level, looking at things like the vacuum or looking at things like the augers, that can get that can be much harder to move if you do have that basically clumping effect of a humidified polymer. So it's definitely worth bearing in mind. How these applications can be, really like looking at that liquid polymer, you bring the drum in, you hook it up, and you kind of like let it go. Yes, you can't store as much on site. You do have it, but if you size your system properly, liquid polymer to me tends to operate more consistently than dry polymer does in general. All right, that's the questions we have for today. I want to thank everyone for joining. If there are any additional questions afterwards, please feel free to send us an email. And again, there will be a quick follow-up poll after this broadcast. Again, I want to thank everybody and have a great summer.